Alright, so let's look at an unsymmetrical alkene where I'm going to subject it to conditions of epoxidation. So the reagent of choice is usually MCPBA. That's metachloroperbenzoic acid. Now the meta doesn't make sense to you yet, but let me go ahead and give you the structure of this. And really the only important part of this is the fact that it's a per acid. In chemistry, per means one more oxygen atom than normal. And so a carboxylic acid is usually COOH, but a per acid is C double bond O, 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 H. And so the key nucleophile, the key electrophile is this extra oxygen. We have a really, really weak oxygen-oxygen single bond, and it's the cleavage of this bond that really drives this reaction forward. So, like in all of these electrophilic addition reactions, you have your pi electrons will attack this oxygen, and one of the lone pairs will then become nucleophilic and attack the other carbon. And while this is all happening, this oxygen-oxygen single bond breaks. This is a concerted mechanism, so this is really happening, don't want to say simultaneous, but it happens in a concerted manner. It's very much like how the alkene attacks a Br-Br single bond to make the bromonium ion intermediate. So at the end of all this business, you're either going to make two oxygen carbon single bonds above the plane, so this can attack from the above. If it attacks from above, it is called psi attack. Of course, that makes me think of Uncle Si in his glass of tea. And if it attacks from the bottom, it's re-attack. So I'm going to show one of the enantiomers. It is geometrically forbidden, and hopefully this makes a lot of sense, that you can't have the oxygen attack one of the carbons from underneath and the other carbon from above. It's not allowed. And of course, this is still protonated at this point. We have a carboxylate, and of course this was metachloro, so here's where your Cl is. Meta just means it's two carbons removed from where the carboxylic acid is. So one carbon removed is ortho, or O, two carbons removed is meta, or M, three carbons removed is para, or P. There's only one para position on the benzene ring. Of course, this would also be an ortho. This would also be a meta. So you'll get into that in more detail in second semester. So right now you have a positively charged oxygen. That's not very stable. So this carboxylate, what I'm going to do is just flip this around. Which was really the leaving group when the OO bond was cleaved. So you can easily envision a proton transfer step right here to generate the epoxide product. And this gives you your epoxide. Plus the enantiomer. Alright, so let's go to a different mechanism. I want to look at hydroboration. Hydroboration, before we even start talking about the mechanistic details, let's talk about what's going to occur. So hydroboration just seems to be one of 3 different ways of converting an alkene to an alcohol. And the mechanism is split into 2 pieces. Number 1, you're going to have a borane. Usually it's B2H6. You can have a sterically hindered borane, but for the mechanism, BH3 works just fine. And this, of course, is in a THF solvent. That's tetrahydrofuran. Tetrahydrofuran is a 5-membered ring, so it is a cyclic ether, and it helps to complex and activate the borane. So this is THF. In the second series of reagents, we have OH minus and we have hydrogen peroxide. Two very critical aspects of this mechanism. Number 1, the regio selectivity. Regioselectivity, when it comes to making alcohols or when you're adding any kind of unsymmetrical addenda, where is the heavy atom going to go? And we've seen Markovnikov addition in almost every single case. Here's one that is anti-Markovnikov. Let's just kind of do a little compare and contrasting with using the mercury acetate, better known as oxymercuration oxidation or oxymercuration demercuration. Oxymercuration will put the OH at carbon 2. It's Markovnikov addition. But hydroboration is going to place the OH at carbon 1. It is anti-Markovnikov. Unlike the oxymercuration oxidation reaction, the hydroboration mechanism also has stereoselectivity. The mechanism really does not account for the stereoselectivity. It is syn addition. And when I say syn addition, I'm talking about the relative stereochemistry of the H that will be added and the OH that will be added. So there are 2 possible products with this reaction, one of which, and even though we don't have a chiral carbon right here, I'm going to show some stereochemistry. Because if the OH comes out, then the H that goes onto the secondary carbon also comes out. If the OH goes in, likewise the H goes in. Better yet, let's look at a cyclic starting material that's unsymmetrical. So this would be a classic way that this would be asked on an ACS final exam. Number 1, the OH is going to become attached to this carbon because it is the less substituted carbon. What I'm going to do is I'm going to try to rotate this in your mind's eye. Picture me flipping this ring so that rather than coming in and coming out, things are going up or going down. And I'm going to show the methyl group going down, which means the H is coming up. That means this OH would also have to come up. And of course, this would be a hydrogen. That's one possibility. The other possibility would be where the methyl is coming up, which means the H is going down, the OH would be going down, the H would be coming up. That's a very classic way of asking this in terms of a multiple choice exam. Okay, so those are the two major consequences of this reaction. And I am not a proponent of memorizing things, but these two details are so important. It makes hydroboration the most important way of generating alcohols in the lab. You must master these two consequences of this reaction. Now let's begin to look at some mechanistic details. Most organic reaction mechanisms have all one-to-one stoichiometry. This one is the one that does not. So I will need 3 equivalents of the alkene plus BH3 I will produce 3 alcohols. I'm going to show one of the stereoisomers. And I will have boric acid as a side product. So here is the overall reaction stoichiometry. All right, so as we start looking at the mechanism, one thing that we need to point out right away is that boron is a larger atom than carbon because it has a smaller effective nuclear charge. And because it's large, it is going, in the transition state, it prefers to interact with the less substituted carbon. What is going to happen in an almost concerted mechanism is that the pi electrons will attack the empty p orbital of boron, and then one of the boron hydrogen bonds breaks, and these electrons are going to interact with a forming carbocation. A carbocation is not formed, so this is in a nearly concerted manner. In fact, if you look at the transition state, you have the formation of a 4-membered ring. This boron is partially negatively charged because it's beginning to make a 4th bond. This carbon is a partial positive charge. So even though it's not a carbocation, we'd rather have our partial positive charge on a secondary carbon rather than on a primary carbon. So 2 things drive this anti-Markovnikov addition. Number 1 is the size of the boron atom, and number 2 is electrostatics. After this reaction is completed, of course this is nothing but nucleophilic attack. Notice I have an alkyl borate, but I have 2 other hydrogens that can also act nucleophilically with a developing partial positive charge. And so this occurs 2 more times. And if we go back and look at the stoichiometry, this now begins to make sense, because I needed 3 alkenes to react with 1 borane to produce 3 alcohols and boric acid. So after this goes through 3 turns, Maybe one too many there. I have a trialkyl borate. Now, one of the things that can occur here is that THF is thought to be implicated in stabilizing this borate complex. Let's take one look at that before we move on to the second piece of this. So, I'm just going to use a blank screen. So if we look at borane through another lens, I'm going to actually show the empty p orbital. Boy, that's terrible. So there's my empty p orbital. And I'm going to show this hydrogen's in the plane. There's another one going into the plane of the screen. And there is another one coming out of the plane of the screen. Then you have THF. So it's going to interact with one of these empty orbitals to provide a Lewis acid-base complex. This is going to be very temporary, and this helps to stabilize the borate so that now the pi bond can interact with the other empty p orbital. I doubt if that's going to be a major consideration in showing the mechanism, but realize the THF really does play an important role in this reaction besides being a solvent. Alright, so in the second series of reactions, hydroxide actually activates peroxide as a nucleophile with a simple proton transfer. And the electrons in this OH bond are now going to be used to nucleophilically attack the empty orbital in boron. This is going to lead to a tetrahedral intermediate. And made one little mistake here. These are not hydrogens, these are the alkyl groups, so let's fix that right away. Okay. So now this peroxide is going to attack, and that's going to give us a tetrahedral intermediate. So now we have boron making 4 bonds. I have the peroxide. Okay, so what's going to happen in this next step is a rearrangement. So we're going to break a carbon-boron bond, and we are going to attack the oxygen that is bonded to boron. And in a very unusual step, now you guys haven't done substitution yet, so you don't know that hydroxide's not a great leaving group, but in this case, hydroxide is the leaving group. And again, this is going to happen 3 times. So 3 times, hydroxide generates a more powerful nucleophile which attacks an empty orbital, which leads to a rearrangement. After that happens 3 times, I have a trialkoxyborane. And again, I'm going to have the same geometry. So this happens 3 times. At the end, I have a trialkoxyborane. So in the last step, this is where things get kind of controversial too. In the last step of this mechanism, I'm going to write these as R groups just to simplify things a bit. So you see that the borane toggles between a trigonal planar geometry in which there's an empty p orbital and a tetrahedral geometry. So now we're back to the trigonal planar geometry, which we have the empty orbitals. And now hydroxide attacks, and the OR group leaves. This happens 3 times, so this is where you get your boric acid. And then RO minus picks up a proton from solution to yield the 3 ROHs. This part of the mechanism is uncertain at best. So I'm going to stop this one.